Welcome back, and in this series of videos we're looking at your moles 2 notes. So if moles 1 was dealing with solids, moles 2 we're looking at gases. So we're going to be looking at the molar volume of a gas, and we're going to be using the equation PV equals nRT. So because the actual size of the gas molecules is very small compared to the overall volume, we can say that 1 mole of any gas, no matter what that gas is, will occupy the same volume at a given temperature and pressure, and we call that the molar volume. So that's the volume occupied by 1 mole of gas under specified temperature and pressure. Now, generally speaking, we use the standard chemistry units of 298 Kelvin and 100 kPa. Don't muddle that up with physics, which generally use 273 K and again 100 kPa. So we basically use room temperature and pressure. So the number of moles is equal to the volume of the gas divided in this case by the molar volume rather than by the RMM. And because we're dealing with gases rather than liquids or solids or solutions, we can say that the molar ratio and the volume ratio are the same, because the molar volume will always be the same number at the same temperature and pressure. So the molar ratio is 1 to 3 to 2, so my volume ratio will be 1 to 3 to 2. So in other words, if I have 10 centimetres cubed volume of hydrogen, so I will need 30 centimetres cubed of hydrogen, and I will make 20 centimetres cubed of ammonia. So again, if I look at another one where I'm doing with all volumes, or mostly volumes, if I look at methane, CH4, reacting with oxygen, gas, to form carbon dioxide and water. If I then balance this up, I need a 2 there and a 2 there. Now that's a gas under standard conditions, that's a gas, that's the gas, and that's a liquid. So I can't use water here because it's a liquid and not a gas. So the molar ratios is 1 to 2 to 1 to kind of blank because I can't use that one. So the volume ratios are going to be 1 to 2 to 1. So in other words, if I've got 40 centimetres cubed of methane, I'm going to need 80 centimetres cubed of oxygen, and I'm going to produce 40 centimetres cubed of carbon dioxide. In my second example, I have ethane, C2H6, again reacting with oxygen to form carbon dioxide and water. Again, I need to balance it. Well, I'm going to put a 2 in front of my carbon dioxide, a 3 there, and I can have halves. It's probably easier to use halves here, so I've got 3.5 oxygens. So the molar ratio is 1 to 3.5 to 2 to 3. Again, because that's a liquid, I can't use it in my volume ratios, but I can use all the others. So if I've got 50 centimetres cubed of ethane, I will need 3.5 times that amount of oxygen. So I'm going to need 175 centimetres cubed of oxygen, and I'm going to produce twice the amount of carbon dioxide. So I'm going to get 100 centimetres cubed of carbon dioxide. So in my next example, I have to combine the equations from the previous topic, moles 1, with our molar volume calculations. So I've got lithium hydride, which is a solid, and it's being used to generate hydrogen gas. So I want to calculate the volume of hydrogen at 298 Kelvin and 100 kPa, or 1 atmosphere, which could be obtained when I decompose or I react 1 kilogram of lithium hydride. So the first thing I need to do is work out my moles of lithium hydride, and that's the same as I did in the previous pack. So I've got mass divided by mR. So my mass, I need to convert it into grams, is 1,000 grams divided by my 7.9, which is my RMM of lithium hydride, and I've got 126.58 227. Notice I'm keeping a lot of numbers in my calculator. I'm not going to round to the last stage. Now the molar ratio between lithium hydride and hydrogen is a 1:1 molar ratio. Therefore, the moles of hydrogen equals 126.58227. Therefore, the volume of hydrogen, well, I'm going to use moles equals volume over molar volume. And I'm going to rearrange this equation to make volume the subject. So the volume is the moles, 126.58227, times by my molar volume, which I'm told either in my data book or in the question is 24. And I've therefore got 3,000 decimeters cubed, and this is to 2 sig figs. The reason it's to 2 sig figs is my data is given to 2 sig figs. So the last example on this page, again, is combining the equations from the previous pack with the ones from this pack. So we're going to heat 21.0 grams of sodium hydrogen carbonate, and we're going to work out how it's decomposing. So we want the mass of the solid residue formed, the sodium carbonate. So I'm going to work out the moles of my sodium hydrogen carbonate, and that's going to be my mass, 21.0 divided by its RMM, which is 84.0, and that gives me 0.25 moles. The ratio between the sodium hydrogen carbonate and the sodium carbonate is a 2:1 or a 1:1/2. So therefore, the number of moles of sodium carbonate is half this amount, 0.25 divided by 2, and that's going to give me 0.125. And then the mass of my sodium carbonate is going to be my moles, 0.125 times the RMM, which is 106, and that gives me 13.25, which gives me 13.3 grams to 3 sig figs. I give my answer 3 sig figs again because my data is to 3 sig figs. Moving on to calculate the volume of carbon dioxide. Well, again, I've got the same molar ratio between the sodium hydrogen carbonate and the carbon dioxide. So therefore, I've got 0.125 moles of CO2. So the volume is my molar volume, 24 times my moles, and I get 3.00 decimeters cubed, again to 3 sig figs. So I can also do this kind of backwards. I can work out the formulae from the combustion values, because if I know the combustion volumes, I'll be able to work out the molar ratios. So I've got 20 centimeters cubed of a hydrocarbon, it requires 100 centimeters cubed of oxygen, and it produces 60 centimeters cubed of carbon dioxide. So I'm going to start by actually writing out the equation. So I know I've got CXHY hydrocarbon, and I know it burns in oxygen, and I know the combustion products are going to be carbon dioxide and water. Now, I don't know how it balances at the moment, but I do know that I need 20 centimeters cubed. This is my volume of my hydrocarbon, needs 100 of oxygen, and it gives me 60 of carbon dioxide. I don't know anything about the water because remember that is liquid under standard conditions. If it was a gas, I could be able to use those values as well. So I know the molar ratio is 2 to 10 to 6 or 1 to 5 to 3 to something. So I know I've got 1 CXHY, and I know it burns in 5 moles of oxygen, and it produces 3 moles of carbon dioxide, and it also produces some water. Now all of the carbon in the carbon dioxide has come from the hydrocarbon. So I can say that X equals 3. Now I can work out, and basically what I'm going to be doing is balancing the equation to work out the hydrogen. So I've got X is 3 because I've got 3 moles of carbon dioxide here. Now in total here I have 6 oxygen atoms, 3 2s are 6, but I've got 10 oxygen atoms here. So I've got 4 oxygen atoms left over. So therefore I must have 4 waters. Now I can work out what Y is, because all of the hydrogen in the water has come from my hydrocarbon. So I have 4 waters, which makes 8 hydrogens, so Y is equal to 8. So I've got my hydrocarbon is C3H8. So we're going to do the next example in exactly the same way. I've got 10 centimeters cubed of my hydrocarbon reacting with oxygen to produce carbon dioxide and water. So again, it's a hydrocarbon. That means it contains carbon and hydrogen only. And it's reacting with my oxygen to produce carbon dioxide and water. I know that my volume ratio is 10, 90, 60. So that's the same as a 1 to 9 to 6 ratio. So I can rewrite my equation CXHY plus 9 O2 goes to 6 CO2 plus some water. So again, X must be equal to 6 because all of this carbon has come from my hydrocarbon. Now I can balance it. Well, I've got 12 oxygens here and I've got 18 here. So that leaves me with 6 waters left over. So I've got 12 hydrogens from here, so Y is equal to 12. So my formula is C6H12. So looking at the last 2 examples on the next page. So again, I have my hydrocarbon reacting with my oxygen to form carbon dioxide and water. I've got my volume ratios, which will give me my molar ratios. I know I've got 5 moles of carbon dioxide, so I've got 5 moles of carbon, so X must be equal to 5. And working out and balancing it with the waters, I get Y is equal to 12, because when I balance it, I need 6 waters here. So my formula is C5H12. And in my last example, I do everything in exactly the same way, only remember I'm going to get an empirical formula. I've been given the RMM of the hydrocarbon, so I can divide that by the empirical formula mass, and I get X equaling 2. And therefore the molecular formula is twice the empirical formula, so I have a molecular formula of C14H20. So in this last bit of the video, we're just going to look at how we can calculate the molar volume of a gas from experimentation. So we're on page 7 of your notes at the experiment to find the molar volume of a gas. So I measured out about 2 centimeters cubed magnesium, and I've folded it into a little U shape. Next, I'm going to fill my burette to the 25 centimeter cubed mark with 2 molar hydrochloric acid. I'm then going to top that up with distilled water. I'm going to put my little bit of magnesium ribbon so it just sits in the top of the burette. Next, I need to invert the burette quickly and place it into my beaker of water, clamp it back into place, and measure off the volume of the liquid. You should see the magnesium there start to bubble away as the hydrochloric acid diffuses through the water layer. It bubbles quite vigorously as hydrogen gas is given off. end of the experiment, I've got a volume of hydrogen gas, which I can then read off. I now know the volume of hydrogen gas and the mass of magnesium that reacted, and I can therefore work out the molar volume of the gas produced. So that just finishes off this section of the notes. So we've looked at the equation moles equals volume divided by molar volume, and we've looked at the little experiment to find the molar volume of a gas. We're going to move on in the next videos to look at combustion analysis and also the equation PV equals nRT. But until then, take care, stay safe, bye bye.